Okay, folks, we should make a start. I guess last time we talked about, or we started to talk about nodal analysis, mesh analysis, Kirchhoff laws, etc. So let's maybe start with a couple of examples for you to think about that kind of demonstrate how this works. So they're from the book, so they're relatively straightforward. So these are nodal examples. So we're going to have so there'll be more problems done on the board in this part of the course because that's illustrative of the techniques you need to develop. So we're going to have a current source, a resistor, another current source, connected together. We're told this is delivering 44 milliamps. This is generating a current in this direction of 10 times Ix. We're just given this as a resistor value R. And we're told the current flowing through the resistor Rx is given by Ix. So the question here is, what is Ix? Equals what? Okay, so any thoughts on how we do this? Can we solve this? No? Yes? Well, it's nodal analysis, so let's look at this node here. What does Kirchhoff's current law tell us? Sum of all the currents going into that node equals 0. So can we write down an equation for what's going into that node? And therefore the answer is it's only 3 currents going in or coming out. 44 milliamps going in, Ix coming out, 10 of I of x coming out. So how much coming out? 11 Ix. So Ix is 44 over 11. 4 milliamps. So that one you can almost do in your head, but let's just write that down as an example. So consider the node, let's call it A. So at node A, all the currents flowing into that node must equal 0. So we can write down an equation that says 44 milliamps. Well, we know that's flowing in this direction because this is a current source. It's got an arrow telling us which direction the current is flowing. So I know I have 44 milliamps going that way. I know this one is producing 10 I of x, and I know Ix is defined as the current through this one. So I know what's flowing out has to be Ix plus 10 Ix, and that is 11 I of x. So I can write down an equation summing the currents together. So that's a fairly straightforward one. This tells me I of x must be 4 milliamps. So let's look at one more along the same idea. Slightly more complicated circuit. This time we're going to have 4 different elements. We're going to have a resistor, another dependent source generating again 10 I of x. Ix this time is defined by the current through this resistor, Ix. This is called R1. We're also going to have a source pointing down of 120 milliamps and another resistor, and this is going to have 12 milliamps, and this is R2. So the question is, again, the same one, what is IX? Okay. You'll learn a little bit if I write down the answer. You'll learn much more if you try and figure out what the equation would be. So take a couple of minutes and see if you could write out what equation or equations we'd need to come up with for this circuit. And if you want a hint, I would say, well, let's say there's a node here, A, another node at B. Kirchhoff's current laws apply at both nodes. So any thoughts on? Yeah, we don't know what the current between A and B is, but clearly you're going to need that to connect the two sides of the circuit. So we could say, for example, and it doesn't matter which way, and here's the first hint at doing these problems, draw a diagram and then draw the direction of the currents you're going to assume. In this case, I'm going to assume it goes this way, and I'll call this I prime. So I'm going to, for completeness, I'm going to assume there's a current I prime flowing into that node. So I can now write an equation for node A and for node B in this notation. So at A, what do I know? Well, I've got IX coming out, I've got 10 IX going in, and I've got I prime going in. So I could say that I prime plus 10 IX equals IX. So 10 IX plus I prime equals what's coming out. If I go in and out on each side, it saves having negatives and positives. So that tells me I prime equals minus 9 IX. The minus sign tells me that the current is really going the other way, and this begins to be obvious because if I've got 10 IX coming this way, I've got 1 IX coming that way, I must have 9 IX going out in that direction. So as long as you draw a picture and put arrows, when you get a negative, it means the current is going in the opposite direction for how you define the arrow. So you could do this problem by assuming a current I double prime going that direction and write a different equation. That would say 10 IX equals I double prime plus I of X. And you get the same answer at the end of the day. Again, looking at node B, well, I prime, stick with the same dimensions that you're using. So I prime is flowing out. 120 milliamps is flowing out. And that equals the 12 milliamps flowing in. I can move this into here, and it should give me IX equals 12 milliamps. Okay, so 12 minus 120 is 108. 9, this is negative 9 IX, so 108 divided by 9 is 12. So, and the negatives cancel to give me a positive current. So IX is 12 milliamps. Questions?
I solved it, but in a different way, but I got
That's fine, that's just the way I solved it. There are different, the key point, you can define currents and things. We're conserving current around this, so we're looking at the nodes. The other thing, I will talk about this later, and I'll just flag it just now as an example. We've got an example of something we'll meet in a few lectures' time of a supernode. A supernode is essentially if I put a box around these two nodes, I still apply Kirchhoff's laws. The current flowing into and out of this supernode still adds to 0. So maybe I don't need the intermediate step. I can add this one, this one, this one, and this one, and just do in one line. Yeah, so there you go. So that would be called a supernode, and we'll look at that more formally in a couple of weeks' time. Okay, so those are examples of solving circuits using nodal analysis. I want to look at a couple more standards or standard tools. And I guess the way to think of this part of the course is we're going to build up a number of techniques, a number of tools that allow us to solve a circuit problem. And you'll notice in previous exams they give you a bunch of circuits and ask you for a current somewhere or a voltage somewhere, and then you have to go through and solve that. And the key to success is identifying what the circuit looks like, figuring out which tool or which technique you're going to apply to give you the simplest solution, applying that solution to the circuit. Okay, so I'm going to come up with two different standard circuits that are useful, that help us. And the first one is a circuit for voltage division. So let's think of a circuit. I'll look at the circuit we're interested in. It's going to be a voltage source, plus minus. It's going to deliver a certain voltage, V of t, and I'm using the same notation as the textbook here, as much as possible. That voltage source, or battery, we're going to connect to two resistors. And this is R1 and R2. And really the question is, can I work out what the voltage is? Can I work what the voltage is across R1? Remember, voltages you measure across a resistor. You take a voltmeter. What are the properties of a voltmeter in terms of resistance? Infinite. Therefore, it draws no current. Therefore, it measures the potential across what it's looking at. So I'm looking for a voltage difference across R1. So this circuit has got one loop. So if it's got one loop, I know that the current around that loop is going to be the same everywhere. No branches, no chance of it splitting. So I can define a current, and let's say it goes that way, I, which could be a function of t. So this one I'm going to apply Kirchhoff's voltage law, because I've got a single loop. If I walk around that loop, if I start at a point down here, and I walk all the way around the loop, I'm going to be back at the same voltage. That's what his voltage law says. Now to simplify it, and what we do typically when we build circuits and do some analysis, we ground one point. So we've got a little symbol that's like a series of decreasing lengths of line. And basically we say this is V equals 0 down here. So this is 0 volts. So this will be a change of volts. This will be a change of volts, and a change of volts. So we're going to apply Kirchhoff's voltage law. And there's a number of different strategies for doing this. So remember, KVL basically says that the sum of all voltage changes equals 0. So we need to get the polarity of the voltage change correct, and we need to know if it's an increase or a decrease. So there's different techniques for remembering how that's done. One that I remember, just because I learned it this way, if I go through a battery this way, the voltage goes up, because I've set this at 0. I go up. I go through here, so the voltage goes down, because I'm flowing with the positive current, so I get a voltage drop. So if I was to write an equation for going around that circuit, I would say V of t, the voltage through the source, minus the voltage across R1 minus the voltage across R2 equals 0. Another convention that gives me exactly the same result, but in some cases can help, and it depends which flavor your variety. The book tends to say, well, these are positive voltages and this will be a negative voltage. And basically they say, well, if I go through a source from negative to positive, I can count the negative terminal first, I'll call that a negative voltage, and then I'm going to have a positive voltage and a positive voltage. So the book convention would be to say negative V of t plus V across R1 plus V across R2 equals 0. It doesn't make any difference, because if I multiply this by -1, I've got the same equation. So I'm going to get the same result. Depends what convention you feel more comfortable with. I think the book tends to use this one if it goes through a voltage source. If it goes from the negative to the positive through the voltage source, it will call this a negative voltage, and then there's a positive voltage drop across these.
Does the voltage not go from negative to positive when it crosses the voltage source?
Well, we call this 0. We're going to put a wire here, and we'll say this wire at the bottom we're going to ground, and when we ground it, we'll call that 0. So at that point, anything here is a positive, it's a number added on to 0. So with a voltage source, it gives a voltage difference of 3 volts. Unless I make a reference, I don't know if this is 300 volts and 303 volts. I know there's a change of volts here. So in all these circuits, the convention is we'll make an earth or a ground, and we'll attach the bottoms, usually the bottom rail or the rail where most components connect together, and I'll say that I'll earth that, I'll set it V equals 0, therefore everything I'm going to measure with respect to that. That's like saying I'm in this room, so I'm going to measure potential energy with respect to the floor. I don't care that I'm on the 3rd floor. So it just makes the problems a bit simpler to solve. Anyway, whichever approach you use here, you get V of t equals V across R1 plus V across R2. And that's another way of writing it. The voltages due to the batteries equal the voltages dropped due to the resistor. So all 3 approaches give the same equation. Okay. So what does that tell me? V of t equals, what's the voltage across resistor 1? Yeah. I'd like to write it in terms of something I know, or something that's consistent around the circuit. I don't know what it is at the moment, but I know the value of the resistance, and I know the current everywhere in the circuit is the same. So using V equals IR seems reasonable. So I could say that equals R1 times the current, which is a function of time, and the other voltage is R2 times the current, which is a function of time. So I can write in terms of the current then. I can say the current, I of t, is just voltage of t across R1 plus R2. But what I really want is the voltage drop across here. So I know V out equals the current times the resistance. So in any circuit, any element, so this would be a branch, because it's one element. This would be a branch. I could combine them and make it all one branch, but let's leave it as it is. If I know resistance and current, I know the voltage. If I know voltage and currents, I know the resistance. So I can always apply Ohm's law in any branch. So it's the simplest thing we can do. We can apply Ohm's law in any branch. So in that branch, I know V out equals I, which is a function of T, times R2. Because I'm sticking the voltmeter across this resistance too. So substitute this. I can say V out equals R2 over R1 plus R2 V of T. So this is the voltage division rule. Basically it says the voltage coming out at this point between these two terminals depends on the values of the resistors I take here. Depends on R2 and R1. Likewise, I can get the voltage across R1, so I can also say also V across R1 equals R1 over R1 plus R2 V of T. And that second voltage would be the voltage across here. But this is called the voltage division rule, and what it means is I've got a certain voltage across here. I've got the same voltage across both resistors because there's no voltage drop in a wire. So what I'm doing is I'm dividing that voltage between the two resistors. And depending on the size of each resistor, I can change the value of the voltage drop. So for example, if I make this a variable resistor, so this resistor I change by changing the path length or the length of the wire or something in the resistor. So I've got a knob that changes this resistance. That means R1 becomes a variable. So now my output voltage changes as I change the resistance. So if R1 goes to 0, yeah. And that makes sense because the top is then connected through no resistance to the top here, and I've just got a source connected to a resistor, and that makes sense. So by controlling the value of R1, I can control the output voltage. So this gives me a controllable voltage source. So this is what we call the voltage division rule. It applies to two resistors in series connected to a voltage source, and it's a useful one in terms of simplifying circuits as we go forward. Questions? Okay, if that's voltage division, we can look at the analog, which is current division. And the circuit I want to analyze for that is going to be something that produces a constant current or a constant flow of charge. I'm going to connect it to one resistor, and in parallel another resistor. Call this R1, R2. And we can define two currents. We can define the current I1, which may be a function of time, I2, which may be a function of time, and this is the total current I, which is a function of time. So it's current, so it's flow of charge. So when I apply Kirchhoff's current law, I'm going to look at a node and I'm going to sum all the currents into or out of that node. So let's look at this node at the top. Well, I know the current flowing in, delivered by the source. This is an independent source. It always gives the current I of t. So I know I of t into the node must equal I1 of t plus I2 of t. And just to clarify, let's say that's flowing down. That one's also going to flow down. Equals. Well, what can we do about this? Or how would we solve this? If we're trying to solve any problem, we want something that connects different pieces of the puzzle together. In the previous one, it was a single loop, so we knew around that single loop the current was always the same. In this one, which is the same as how we work out potentials, we know the voltage across R1, voltage across R2, and the voltage across the current source are all same. So yeah, so the voltages are all the same. So now I can apply Ohm's law and say that this would be V of t over R1 plus V of t over R2, which is just 1 over R1 plus 1 over R2 V of t, or V of t over R parallel. So 1 over R1 plus 1 over R2 is 1 over R parallel. So I've added 2 resistors in parallel. So that tells me that V of t is equal to Rp times I of t. Okay, so I've just taken that term and this term and rearranged it to make this equation. R of P is? So it's 1 over R1 plus 1 over R2, but I gave you a handy reckoner for what that would be. It was the last thing I wrote down on Monday.
Oh yeah, R1 divided by R2 divided by R1.
R1, R2 over R1 plus R2 equals RP. Times I of t. So R of P equals this thing. So make sure you prove that to yourself, because that's a useful thing that will short circuit calculations when I've got parallel combinations of resistors. Okay, so I know what the voltage is now in terms of the combined resistance and the current flowing into the circuit. So now I can work out what current in branch 1 and the current in branch 2 would be, because I have these relationships, because I know this equals and this equals. So I can say I1 of t equals V of t over R1, so I1, substituting in for V of t, I end up with R2 over R1 plus R2 I of t. And similarly, you can show I of 2 is R1 over R1 plus R2 I of t. So current in branch 1 depends on resistance in 2, current in 2 depends on resistance in 1, both divided by the total resistance. So again, you've got a circuit where the current flowing through these two branches depends on the value of R1 and R2. So if R1 and R2 are equal, the current in each branch should be the same. Does that make sense? So if all equals R, this would be R over 2R. The R's cancel, it would be 1 over 2, so I'm dividing half the current into one of the branches. So if I've got two equal resistors in parallel, driven by a current, I get the same current through each. Likewise, if I make one of these a variable resistor, sign for a variable is having an arrow drawn through it, I've got a variable current source. So the current through R2 changes as I change the value of the resistance R1. So the current through 2 changes as I change the value of 1. Likewise, maybe I'd be better changing this one if I want to do 2s. But I could change either, but I balance the currents. I'll change the currents. So if one of the resistors goes to infinity, the current through the resistor is 0, so it all goes through the other. If one of the resistances goes to 0, becomes what we call a short circuit, all the current flows through the short circuit. And again, those two equations confirm that. So these two rules, current division and voltage division, are useful when you're looking at combinations of series and parallel resistors, because they'll help you simplify the following circuits. So let's look at one to finish. Well, any questions on this? Good. It can be N, so I can add another 2 or 3 resistors and I still get the same thing. So here's a question for you. So let's take a source that's delivering a constant current, and let's connect it to, well, let's consider a battery actually, so it's plus minus certain voltage, and I'm going to have some lamp bulbs. And I'm going to draw those as so these things are your Christmas lights, or your lighting circuit. And I place a switch in this. Place a wire down here, and I have a switch. So the question is, what happens to the intensity? Because clearly in this circuit, it's a connected circuit, so all the lamps are on. If I close the switch, what happens to the lamp, the intensity of each of the lamps? And I've got 3, which I'll call A, B, and C. Well, think about it. Talk to your mates if you want. Yeah, somebody else at the right. Okay, so I close the switch, C turns off. You happy with that? I'm making a short circuit, so this is essentially really resistors. So the lamp is a resistor, so it's high resistance, so it heats up a lot and generates light, or it's an LED or something. So the voltage drop as I go through. So in the original circuit, I go through 3. I'm going to have some current flowing around the circuit. Close the switch. Resistance of this line is 0. No current flows through here, so C turns off. So what about the intensity of A and B? Increases? Same. Well, this is constant current, so it produces a certain voltage. I know V equals IR. Total resistance of the circuit, the new circuit after I close the switch, is less because I've switched one of them out. The circuit I'm interested in now is through A, B, and through this route here, because this is a short circuit. If there's a short circuit, it doesn't matter what's across here, none of the electrons get into that side. So the resistance goes down, current goes up, so the power dissipated, V times I, goes up. So lights get brighter. So one goes off and two get brighter. Where were we? Okay, so that's a conceptual question. Let's do a more traditional circuit type. Problem. So I'm going to have a voltage source, plus minus, and that's going to be 12 volts. It's going to be connected to some resistors. This one will be 20 kilo ohms, 30 kilo ohms, 40 kilo ohms, and 20 kilo ohms. And the question is, if I place a voltmeter here, what's the output voltage I would measure? So I know the input voltage. I know a bunch of resistors. But what's the output voltage? So how could you do this problem? That's one way. If I knew the current through that 20 kilo ohm resistor at the right-hand side, I'd know the voltage. So that would be an idea, if I knew the current flowing through this circuit. But I can't easily get the current because I don't know yet what that current would be.
What about if I'm equivalent resistance? Does that work?
Yeah, well, in this one it does work because I can see these two are in series. This new one is in parallel with this one, and this combined one is in series with this one, so I could work out R equivalent. So this is a relatively straightforward one. So I could say, well, let's say label these. So this is 1 and 2. So R12 equals 40 kilo ohms plus 20 kilo ohms equals 60 kilo ohms. 60 kilo ohms is going to be in parallel. And if you want for this one, I can just quickly draw what I've done there. I've got the source, the 20K resistor, haven't touched the 30K, but now I have, this is 60 kilo ohms. So I've made the circuit look like this. I've combined two resistors. So I've now down to 3. So next step is combine these two in parallel. And if I call that 1, 2, and I call this one 3, I would call this, just to track what I'm doing, R1, 2, 3. Because I might need these individual numbers later on. So I've got 30 and I've got 60, so that's going to be 30 times 60 over 30 plus 60. I think equals 20 kilo ohms. Well, it looks like 180 18, well, it's 18 over, yeah, 9, so 220, 20, yeah. Okay, using my trick of how to do 1 over, I can simplify that calculation. And finally, the final circuit, R total equals the 20k plus the 20k, which is the rest, equals 40 kilo ohms. So this circuit is the same as plus minus 12 volts into 40 kilo ohm resistor. So that's the equivalent circuit. So I know R, I know voltage, Ohm's laws come in, I now know current, so I can say V equals IR, gives me current equals 12 volts over 40 kilo ohms equals 0.3 milliamps. Typical values, just so you know, is a resistor of 1 ohm is quite a low resistance. If I've got a resistor of 1 ohm, a voltage of 1 volt, I'm drawing a current of 1 amp. Typically, I use much higher resistors. I use kilo ohms because then it's significantly higher than anything that might be wiring or soldering or anything in the circuit. Therefore, I can ignore all that because it's such a low resistance. The biggest components are the large kilo ohm resistors. If I've got voltages in volts and I've got kilo ohm resistances, I usually have currents in milliamps. So clearly 10 to the 3, 10 to the minus 3. So I know the current is 0.3 milliamps. That's the current flowing around this circuit. I equals 0.3 milliamps. Now I have to walk back through the problem. This is where voltage division and current division might help us. The current flowing through here, I, is also 0.3 milliamps. Okay, so the current leaving the source is 0.3 milliamps. Current going through this resistor must also be 0.3. I don't know what happens over here yet. So now really what I need to do is back out the problem, so I guess if I draw in the step that I missed quickly, this was 20 K and this was 20 kilo ohms. So I simplified these two to give that circuit, then this circuit, and then back to this circuit. So that was the steps I went through to simplify the problem. Now to work out the output voltage, I need to go back through the problem. So this is 12 volts. So what does this look like? This is voltage division. Two resistances are the same. They have the same voltage. So 6 volts across each of them now. So, okay, this is beginning to, so I know the voltage across this one, 6 volts, and the voltage dropped across here is 6 volts. And that should be consistent with this current flowing as well. So if I go to the problem at the circuit at the top right, let's redraw that slightly differently. That's got plus minus, that's 12 volts. And I'm going to draw it like this. So that's essentially the same circuit as the top right. I've just moved the resistor around. And I know that the voltage across the first resistor is 6 volts, and I know across this parallel combination the voltage drop is also 6 volts. That's what I did in the bottom right over there. So this is my 20K. This is my 30K. And this I think is my R12, which equals 60K. So I know V prime, let's call it here, is 6 volts, because these are the same. However, what I need is the voltage across the 20K. So I need to rewrite this circuit one more time. So where can I draw that? Let's go here. So if I draw it as 12 plus or minus, I've got this is 20K, this is 30K, this is the original circuit, which is 40 and 20. And my original problem, if I go back, was what is the voltage out at that point. Okay, so I've just redrawn it. It's the same circuit, I've just moved the components around a bit. But if I work back through that circuit, I can apply the voltage division logic that this is 20 ohms, this parallel combination is 20 ohms, so I know this is 6 volts and 6 volts. So I know between this point and this point, I've got 6 volts. So I'm applying 6 volts to a series combination of 40 and 20K. So I can use the voltage division rule that I came up with a few moments ago. And that tells me V out equals the 20K, over which I'm measuring the voltage, divided by the total, which is the 20 plus 40, multiplied by the voltage I'm dropping across the whole thing, which in this case is 6 volts. So V out should be 2 volts. Okay, so I'm running short on time, so maybe I went a bit quickly. Let's just quickly recap on what we did. We simplified this circuit, series parallel combinations. That gives me one resistor. Across that one resistor, I know I dropped 12 volts, and it's across 40. I can work out the current. But I can also know that I know the voltage current division rules. In this case, I've got two 20s in series. Voltage division tells me same voltage across both. So 6 volts and 6 volts. That translates into, sorry, it's across this side now, this circuit, where this is, or maybe this circuit, this one's 6 volts, this is 6 volts. I recombine the circuit and make it bigger, this is still 6 volts, and this voltage here is still 6 volts. So now I've got two resistors in series, which have a 6 volt potential drop across them. I apply the voltage division rule, because they're different, and I get 2 volts. That's the final voltage. So it's a quicker way of solving that. Now you could work out the current, and you could work through the circuit, and at each stage you could work through current resistances and work out voltages, and I'll leave that for you to check, but you should end up with the same result at the end of the day. So current and voltage division rules can help simplify these circuits. Okay, thank you.